And so to talk a little bit more about how we're going to have the robot sense its own environment, embodiment, and information about its sensors, I'm going to hand this over to John Kelly.
Hi, thanks Ross very much. Good afternoon everyone. My name is Jonathan Kelly, and I'm a PhD candidate in the Robotic Embedded Systems Lab at USC. We actually all share space on the same floor. There's 3 labs on the same floor of our building. This is a picture of our lab group. We're currently, our main PI, 10 PhD students and 2 postdocs at the moment. And as Ross was saying, one of the things we discussed earlier today, or earlier yesterday as well, was calibration, sensor calibration. Of course, the PR2 is a very sensor-rich platform, something that we're looking forward to using for that reason. And sensor fusion is one thing we'd in particular like to do. So I've shamelessly stolen these pictures from the calibration tutorial slides. And so, in particular, in the area of sensor fusion, we'd like to do things like fuse IMU motion estimates with wheel odometry, and then register laser and camera data all at the same time. And so in order to do that, normally what you would do is initially when you start your robot up, you would perform the calibration steps that we went through the other day. You would use a planar calibration target to calibrate the cameras. You may also calibrate the laser. You would calibrate the transforms of the various sensors. Of course, one of the things about this is that it takes a long time. It's tedious. No one enjoys doing it. You'd rather do other things, learning, etc., planning, so on. So what we're looking at doing, actually, is hopefully alleviating the need to do this directly. So removing the need for a target. And so with that in mind, we're looking at developing a package that we've just tentatively called POGO, which stands for Power On and Go Robotics. And the idea is essentially to enable online, continuous, autonomous self-calibration of the sensors on board the PR2, as well as other robots that will be used with the ROS package. This will be released as either a package or perhaps a stack. And so a number of the things we're looking at calibrating the camera intrinsics and extrinsic parameters, so maintaining stereo calibration online by running a background task, essentially, on your PR2, which would do this for you. So if you're driving over rough terrain or rough ground, for example, lots of carpet where the robot is jiggling a lot, we'd like to maintain stereo calibration automatically for you. Another thing we have to calibrate is the internal transforms, the 6 degree of freedom transforms between the IMU and each of the cameras, as well as the laser. And also to calibrate systematic errors in wheel odometry, so to account for any wheel error or wheel wear, etc. And one of the things that we've recently just started thinking about is using the texture projector on the PR2 as part of the camera calibration, without a target, without a planar target, but actually projecting that texture onto the environment itself and using that for calibration. So hopefully we'll have this available for the community in the near future, and we'd be very interested to get your feedback. And so of course, once you have calibration, your robot is calibrated, you can then go ahead and do some other interesting things like learning and motor control. And with that, I'll hand it off to another student, Ludo.
Hi. So on the other side of the corridor, there's the Computational Learning and Motor Control Lab, headed by Stefan Schall. These are the people who work in the lab and are going to develop code for ROS and for the PR2. And we're mainly interested in motor control. And our main approach and main contribution we'll do for the ROS and PR2 are dynamic movement primitives to do mobile manipulation. So the idea is that you can teach a robot to do some task. So this demo were done last fall by Peter at Willow Garage during the internship. So all this code already exists for us. So the idea is that you can teach the robot to do some task, and then the robot is able to replicate the task. Then you can build a library of such movements, and the idea is to be able then to sequence these movements together and to have online adaptation of these movements so that we can achieve complex behaviors. So the nice thing that comes for free with this idea of movement primitive that we developed, these frameworks, that we can automatically generalize the movement that you're doing, and for example, if we change the goal where the glass is, change the goal where the bottle is, the robot is able to automatically online reprogram its plan to follow the new target. So there is no need for replanning. Everything is done online, and it's part of the framework of these primitives, which is pretty convenient to have a very to already generalize movement primitive, as you can see in the video. So all these things already exist for us. So the other thing we're interested in is to be able to add obstacle avoidance, to be able to online change the behavior of the primitive. So for example, you teach the robot to do one movement, and then it's able to automatically change its plan to avoid an obstacle, for example, and to finally reach the goal we ask it. And we're also going to look at reactive grasping, or how you can modulate the grasp online depending on sensor information that you get. These are ongoing research, and this is going to be integrated now on PR2 and in ROS. So far we teach the robot to do one thing, and is able to do it and to generalize, and also to avoid obstacle and do very simple reactive planning. But it's not robust. So there is no robustness beyond that, and we would like to improve these policies using reinforcement learning. So we have recently developed an algorithm which is called pi-square, which is a policy improvement using path integral, which is a trajectory-based reinforcement learning algorithm. So the idea is that you have your initial policy that you teach the robot, and then we can improve this policy to achieve different goal, to improve the robustness of the policy. So usually when you teach with a kinesthetic demonstration, the robot knows only, well, the joints movement, but you cannot really, there's a lot of things you don't see in this you cannot perceive in this demonstration. So the idea is to use the reinforcement learning to be able to learn all these things that you cannot teach by kinesthetic demonstrations, to improve the robustness, and to also, for example, to relearn the redundancy resolution you want to have for your manipulation task. So you see here the demonstration of learning with the little dog in simulations. On the left, this is an original jumping behavior to cross a gap. This was taught by a human, and then we learned, we send the algorithm, and then at the end on the right you see what the robot is able to do after learning. It's able to cross the terrain with a very high success rate, which was not the case for the initial demonstration. It not only works in simulation, it also works pretty efficiently on a real robot too. So that's the goal, is that our algorithm works on a real robotic platform and can do online learning on things on a real robot, which is not so obvious for many machine learning algorithms. So we would like to have that on ROS and on PR2 and see how far we can go with that. So far I talk only on you learn movements, and you basically you do like trajectory, you generate trajectories, and you assume that your robot is able to track your trajectories either in Cartesian space or in joint space, anything. The second thing we would like to work on is motor control. So we would like to have more compliant behavior. So for example, when you see the robot jumping, we need compliant control. If you have eigen PID controller, it will never work. You need like more advanced nonlinear torque control controllers. So the idea is to provide PR2 the ability to have a compliant and variable stiffness control. Also, we'd like to do some force control, but okay, we'll need some force and torque sensing at some point to do that. And we'd like also to use machine learning techniques to be able to learn these controllers automatically. So using, for example, the pi-square algorithm I've shown you before, we already have preliminary results on different robots where you can basically learn a variable stiffness control for different kind of movements. And that's about it. So we would like to thank you, Willow Garage, for the crazy workshop and for giving us a PR2 robot. So, thank you.